Welcome everyone. Today's presentation will be on hybrid electric vehicle control optimization using PC and cloud-based parallel computing. My name is Kevin Oshiro, and I will be your first presenter. I am a senior application engineer at MathWorks based in the Seattle, Washington area. Previous to MathWorks, I worked at PACCAR's Kenworth Truck Division as a research engineer developing hybrid electric powertrains for medium and heavy-duty vehicles. I also hold a master's degree in electrical engineering from the University of Washington. I'm also here with Ryan Kladney, who will be your second presenter. Ryan?
And I'm Ryan Kladney, also a senior application engineer at the MathWorks Novi, Michigan office. My previous industrial experience includes hydraulic control design, simulation, and testing for ultra-class hybrid electric mining shovels with Caterpillar Global Mining, and as a mechatronics and actuator scientist at ABB's German Corporate Research Center. I also hold a PhD in mechanical engineering from the University of Alberta.
Thank you, Ryan. Let's start today's presentation with a general problem statement. How do you design a hybrid electric vehicle and maximize its fuel economy? It is a very difficult problem with many considerations. There are architecture and hardware selections. For example, serial versus parallel versus power split architectures, or the sizing of an electric machine or battery pack. You have to account for many drive cycles, operating modes, and markets. There are complexities in modeling plant and controller systems. You have to be concerned with real-time deployment for hardware in loop or target ECUs. And you have to optimize the performance of your system. Hopefully, during today's presentation, we will give you a process or workflow for your own HEV development and optimization. Next, I would like to discuss the powertrain architecture we studied for this presentation. It is a multi-mode design outlined in the SAE white paper listed here. This is the powertrain in the 2014 model year Honda Accord Hybrid. The multi-mode hybrid can operate in 3 discrete operating modes. In the electric vehicle mode, a battery pack and electric motor provides traction and regenerative braking to the front tires. This mode is used for lower speeds and lower power demands. In the serial hybrid mode, an engine is the prime mover for a generator that provides extra power to the high voltage bus. The front tires are still only driven by the electric motor. This mode is used for higher speeds and higher power demands. The engine mode is where a mechanical clutch can couple the engine directly to the wheels. The electric motor can still be used to provide torque assist or regenerative charging. This mode would only be used in higher speeds and lower power demands, such as highway cruising. We chose this powertrain architecture because it is fairly new to the market. It is also an elegant design, as there is no multi-speed transmission and the battery energy capacity is fairly small at 6.7 kilowatt hours. These multiple operating modes provide a challenging task for designing and optimizing a supervisory controller. I am now going to switch over to the Simulink model so you can see how we modeled the multi-mode powertrain and controllers. This is the Simulink model of the multi-mode powertrain. The bottom half of the model includes plant subsystems for the engine, the generator, the battery, the DC-DC converter, the motor, and the vehicle, which includes the longitudinal vehicle dynamics, friction brakes, and tires. I will go through these plant subsystems in more detail later in the presentation. The main input to the model is a speed versus time drive cycle, which is located here. We loaded several industry standard drive cycles, such as FTP75 and US06. You could enter in your drive cycle as well. The drive cycle signals then go to an operator or driver model. The driver model consists of a state flow chart and 2 PI controllers, one for the accelerator pedal and one for the brake pedal. The state flow chart determines if you are stopped, accelerating or cruising, or braking. This driver system is attempting to track the drive cycle speed reference using the simulated vehicle speed as a feedback signal. The accelerator and brake pedal controls will minimize the error between the desired reference speed and simulated vehicle speed. The accelerator and brake pedal commands then go to the controller system, which is implemented as a model reference. We use the model reference because it allows for modular development by several engineers. You can use it for IP protection, and it also enables faster simulation. Inside the controller model, there are 2 subsystems, one for power management and one for multi-mode supervisory control, which is implemented via this large state flow chart. I will cover these systems later in the presentation. I will now hit the play button so you can see this model running over a standard USO6 drive cycle. I will also bring up a couple of figures that we can look at while the simulation is running. The first figure is the speed and state of charge as a function of time. The top vehicle speed graph shows two signals. The blue signal is the reference signal from our drive cycle block, and the red is the simulated vehicle speed. You can see that the model is able to track the desired drive cycle quite closely. The vehicle starts off in EV mode, and you can see the SOC of the battery decreasing during the initial acceleration event. The second figure we will look at is the requested tractive force versus vehicle speed. This figure will be a major topic of discussion for the optimization portion of our presentation. The requested tractive force is the signal that is coming from our simulated accelerator pedal. This figure is outlining different requested power regions for the three discrete operating modes and are partitioned as shown. EV mode is used at lower speeds and lower power demands. At higher speeds and lower power demands, the engine/power split mode is used. And at higher speeds and higher power demands, serial hybrid mode is used. The star and comet trail shows the instantaneous operating point of the simulated vehicle as it is driving. There is temporal logic built into the state flow chart to keep from transitioning into and out of the modes too quickly. I will now open up the Simulink Data Inspector so we can look at the types of internal signals the model is generating. We can look at data such as the state of charge, the voltage of the battery pack, the power of the battery pack, and the current of the battery pack as a function of time. We can also look at energy consumption of both fuel and battery. This model then becomes a very important tool for performing system-level simulations of your hybrid electric vehicle design. You can dynamically simulate your system and see if you are meeting your design and performance requirements. An optimization study was performed by Ryan on the multi-mode supervisory control regions. Varying the EV, serial, and engine regions has a significant effect on the overall energy consumption of the vehicle. The optimization study was able to adjust the different operating regions and yielded a 9.4% improvement in MPGE, which is quite substantial. MPGE takes into account both the fuel and battery energy consumption. And the engine power split mode was found to be more efficient at higher speeds. The optimization problem is computationally intensive. However, through PC and cloud-based parallel computing, Ryan was able to reduce the optimization study from 27 days to half a day. The key points we would like you to take away after this presentation are: MathWorks tools can facilitate rapid HEV system design and control development. We can maximize HEV efficiency through supervisory control optimization, and we can accelerate the optimization process via parallel and cloud-based computing. I will now cover the system-level plant models in more detail. We can use a variety of MathWorks tools to create the plant models of the multi-mode powertrain. Please keep in mind the basic trade-off of modeling and simulation, which is balancing model fidelity versus computational time. In general, adding more model complexity or detailed dynamics will increase your simulation time. Some of the models I'm about to show have variant subsystems, which allows us to use varying levels of model fidelity in order to balance this trade-off. Let's begin by looking at the electrical plant models. The battery was modeled using two different methods. The abstract model is based on a charge-dependent source with internal resistance. This is a standard block from the SimPower Systems library and was parameterized to represent the entire battery pack. A detailed model of the battery uses SimScape to model an RC equivalent circuit with thermal and SOC dependence for each cell in the pack. The cells are then wired together to form the desired pack configuration. For this model, we had 100 cells in series. We can also use this abstract versus detailed modeling technique for the electrical machines and inverters. For the abstract model, we can use the servo motor block from Sim Electronics, where you can parameterize the maximum torque versus speed curve of the combined motor and inverter set as shown in this figure. We can also couple this to an efficiency map to account for losses. The electric machines and inverters can also be modeled using a detailed method via sim power systems. The permanent magnet synchronous machine block was used for the detailed model, as well as individual IGBTs to create an inverter bridge, including a controller to perform the high-speed switching. For the DC-DC converter, an abstract model from Sim Electronics was used. I'm now going to switch back to the Simulink model so I can show you the electric plant model systems in more detail. Let's start with the battery. Note that we use the variant subsystem, so we can have two separate models located in the same system. You can then select which variant you want to use. Looking inside the generic or abstract system, we can see a simple model represented by this battery block. It is parameterized using values found on a battery spec sheet, such as nominal voltage, amp hour rating, and internal resistance. This model is intended to represent the entire battery pack. The abstract model is ideal for performing high-level system-level simulations and optimization studies where faster simulation speed is desired. I'm now going to switch over to the detailed variant model. Inside the detailed model, you will see 10 modules wired in series. Inside each module are 10 cells wired in series, for a total of 100 cells wired in series for this pack. Let's look under the mask of one of the battery cells. We can see here the RC equivalent circuit topology, where each component in the RC circuit is a function of temperature and SOC. You may recognize this model from previous white papers and webinars from mathworks.com. This detailed model is ideal for studying cell-to-cell, electrical, and thermal interactions, but it will run slower due to the increased fidelity. Now, let's look at the electric machine and inverter variant subsystem, which contains an abstract and a detailed model. In the abstract model, we use the servo motor block here. You can see the parameters that are needed, such as the maximum torque and speed vectors. I've also added this external efficiency map implemented using this 2D table. You can then account for the electrical losses and place the losses back onto the electrical bus. I will now select the detailed model. In the detailed model of the electric machine and inverter, we use blocks from the Sim Power Systems library. Here is the permanent magnet synchronous machine block. If you click on the Help button, the document will outline the first principle of physics used to model the dynamics of this machine. In this system, we also modeled the individual IGBTs in a 3-arm bridge. If you create a detailed inverter model such as this, you also have to create a controller which will perform the high-speed switching signals for each IGBT. Now I would like to discuss the mechanical plant models. The engine was modeled using our model-based calibration toolbox. This is a high-fidelity statistical model with numerically optimized parameters. This is the only plant model where we did not use one of our SimScape physical modeling tools. Engines are complex and difficult to model using first principle equations, and using a statistical model is very common in the industry. Also note that we did not have access to the engine listed in the SAE white paper, so we had to use data from a previous project on a much older engine. The powertrain is modeled extensively using our Sim Driveline library blocks. This includes the longitudinal vehicle dynamics, where you can specify the mass of the vehicle, coefficient of drag, and frontal area. There are several blocks to model the tires. One we like to use in particular is the Magic Tire Formula block. We can also model the friction brakes, the differential and gears, and the dog clutch that connects the engine to the drive wheels. We also model the cooling system using the SimScape Thermal Liquid library. The motor, generator, and battery have liquid cooling circuits attached to them, and we can model the conductive and convective heat transfer from each component. I will now switch back to the model so you can see the mechanical plant models in more detail. Inside the engine plant model, we use the model-based calibration toolbox to create these lookup tables. These lookup tables contain the dynamics of the engine. Inside the vehicle plant model, we have the entire drivetrain modeled. The vehicle body block contains the longitudinal vehicle dynamics, and you can parameterize the vehicle mass, the coefficient of drag, and other geometries here. The left and right tires of both the front and rear axles are included, as well as the friction brakes for each wheel and the front differential. The cooling system contains the cooling circuits for the generator, the battery, and the motor, as well as the cooling pump and fan, and the main heat exchanger. Another topic I would like to discuss is how we partition the model by physical domain. You may have noticed that we have multiple SimScape local solver blocks in the model. Each local solver block runs on a different fixed time step. The blue boundary contains the mechanical system partition, which includes the engine, clutch, and drivetrain. A 2 millisecond time step is used. The green boundary contains the electrical system partition, which includes the electric machines and inverters, batteries, and power electronics. In general, batteries and the motor's inverters have the fastest dynamics, so 1 millisecond time step was used. Conversely, in the red boundary, the thermal system partition runs at a 100 millisecond time step. This is because the dynamics of the thermal system are much slower than that of the mechanical or electrical systems. The controller was implemented using a 10 millisecond time step. Partitioning the model allows for more efficient computation and makes it much more scalable for use with real-time hardware. For example, we worked with DSpace and implemented the partitions exactly as shown, where each partition ran on its own processor in a hardware-in-loop environment. The next topic I would like to discuss is power management. Power management is a very important aspect of hybrid electric powertrain design. You want to manage the power into and out of the battery pack to ensure safe operation and extend battery life. I will show a diagram of a feed-forward control algorithm for the motor, which works for both traction and regen. The objective of the algorithm is to bound battery power between its dynamic discharge and charge limits, which are a function of SOC. We first start at the accelerator or brake pedal signal. This can be scaled by the motor torque speed curve to produce a torque request. We can then use the efficiency map of the motor to estimate the electric motor power request. We can now estimate the total battery power request by adding up the electric motor power request and the electric accessory power, the estimated battery I²R losses, and the generator power if in serial hybrid mode. Now we can do a comparison of the total battery power request to the instantaneous dynamic battery power limit. If the total battery request does not exceed the battery limit, we can allow the initial torque request to go to the motor. However, if the total battery request exceeds the battery limit, we have to calculate the allowable torque request by working the problem backwards. We will start by using the battery power limit and subtracting the electric accessory, I²R losses, and generator power. We can then use the efficiency map to determine how much allowable mechanical torque can be sent to the motor. In the following figures, I will show example results of the power management algorithm. Let's look at this portion of the USO6 drive cycle. The vehicle is accelerating, then slowing down and braking. This figure shows the torque requested and allowed during the acceleration and deceleration event. The torque requested is the blue signal, and the torque allowed is the green signal. When the requested and allowed torque signals do not overlap, it indicates that the battery limits would have been exceeded. This happens for both positive torque or traction and negative torques or regen braking. An example is seen during the end of the deceleration event. Requested regen braking was not allowed because the battery could not accept the charge. Finally, you can see the instantaneous battery power as well as the dynamic power limits of the battery. Note that during this acceleration and deceleration event, the battery power is bounded between its limits. This happens even when the vehicle is transitioning between EV and serial hybrid modes. Bounding your battery power will also bound your battery currents and keep the high voltage bus stable. Finally, I would like to discuss the multi-mode controller. As shown previously, the top figure shows the different operating modes, which are based on the requested force from the accelerator pedal and vehicle speed. The multi-mode control was implemented using stateflow and embedded Simulink functions to manage the mode transitions, and temporal logic is used to keep the modes from changing too rapidly. Here is an example of how the multi-mode control transitions between states. Let's say the vehicle is in serial hybrid mode and transitions into the engine power split mode region. This will cause the top-level model control chart to transition from the SHEV state to the engine state. Simultaneous transitions will also occur in the lower-level engine and generator control charts. The engine will transition to a state to wait for the clutch. The generator will transition from SHEV mode to a speed match mode. This state contains an embedded Simulink PI controller that will use the generator to match the speed of the engine to the wheels before closing the clutch. When the speeds are matched to a specified tolerance, the clutch is closed. Once the clutch is closed, the generator transitions to an off state, and the engine transitions to an engine drive state that allows power split with the motor. Power split with the motor allows the engine to operate at its most efficient BSFC points. The motor can be used as a trim control to provide torque assist or charging, and keeps the engine operating point from moving off its ideal operating line. So, thinking more about the multi-mode control optimization problem, the operating boundaries have a significant effect on energy consumption. What are the best boundary shapes? And how do you optimize and scale this problem? This is a very difficult problem, one that probably couldn't be done manually. Luckily, I work with Ryan Cladney, who is an optimization expert. Ryan will now discuss how we found an optimized solution.
Thanks, Kevin. For my portion of the presentation, I'll be providing a high-level overview of the optimization and parallel computing techniques used to maximize the simulated fuel economy over a US-06 drive cycle. Revisiting the supervisory controller mode transition chart, it will hopefully be apparent that the operational point at which a mode transition occurs, or the shape of the mode boundaries, will have implications on the overall vehicle efficiency. Therefore, we're going to want to automatically adjust the boundaries of these regions to maximize the equivalent miles per gallon. In this case, we're defining equivalent miles per gallon as the total drive cycle distance divided by the total equivalent amount of energy used in order to account for the energy stored in the battery. This is our single objective that we're going to have the optimization algorithm maximize. Constraints in this case are going to be practical in nature and include a DC bus voltage and current limit, absolute and cumulative tracking errors, and a maximum 0 to 60 time. Instead of defining the mode transition curves through tabular points, I've greatly reduced the design space by defining the boundaries as analytic expressions. For example, this function FD defining the EV to serial hybrid electric vehicle mode as a function of beta, gamma, and alpha, and the overall vehicle velocity at a given instant in time. While this will not provide for completely arbitrary parameterization of the transition map, these curves will be sufficient to capture the steady-state power capabilities of the motor and engine while simultaneously simplifying the search problem. With these 5 design variables, beta, gamma, alpha, psi, and kappa, the internal constraints that I mentioned, and a single objective defined, let's take a closer look at the key elements needed to solve this optimization problem. We're going to maximize the fuel economy over a US-06 drive cycle. This drive cycle was chosen as it will induce a rich set of operational modes as a result of its aggressive acceleration and braking profiles that it contains. Kevin has already demonstrated where in the Simulink model such drive cycles are defined, and in this case I'm also going to benchmark the vehicle's 0 to 60 miles per hour performance prior to the US-06 standard cycle. This will allow me to disqualify design candidates that have insufficient performance or otherwise lead to a constraint violation with minimal simulation cost. In a more extensive study, one would likely want to conduct a robust optimization that includes multiple drive cycles to ensure that the MPGE maximization over a broad set of scenarios has occurred and mitigate any sort of cycle-beating design candidates that may result. Given that I'll need to perform an optimization of a system that contains both software and hardware elements, I'll need representation of both in one top-level model. In this case, I'll use the model that Kevin has already demonstrated, which incorporates both the supervisory controller within that model reference system and the operator and vehicle representations, which are combinations of Simulink, Stateflow, and SimScape components. The top-level model will be compiled and run as a rapid accelerator executable so as to minimize the model update and simulation time over the course of the hundreds of simulations that the optimization algorithm will use it for. Obviously, some kind of algorithm will be needed to automatically maximize the fuel economy. In this case, I've chosen a genetic algorithm, which I'll discuss further shortly, that will be enabled through scripts to vary the design variables, run the model over the combined drive cycle, and post-process and evaluate the resulting performance. Aside from such a cost function script, I've also defined scripts to invoke and coordinate parallel computing tasks such as the creation and submission of batch jobs to a variety of cluster resources. I also have a couple of scripts to assist with the collection and visualization of the optimization results. Since Kevin's already covered the HEV model, let's go into a little more depth on the optimization algorithms available in MATLAB. The MathWorks has two MATLAB toolboxes for solving optimization problems, the Optimization Toolbox and the Global Optimization Toolbox. The differences between the two solutions are summarized in this slide. The Optimization Toolbox contains the widely used solvers that use gradient-based methods for searching the solution space. These solvers tend to be very fast at finding local solutions and can scale to high-dimensional problems. When compared to the solvers in the Global Optimization Toolbox, they can reach a solution with fewer function evaluations. Of course, this assumes we don't have multiple maxima or minima located in close proximity to our initial starting point. In contrast, Global Optimization Toolbox is well suited for finding global solutions most of the time. Finding global solutions is a challenging problem, and the solvers in the Global Optimization Toolbox certainly increase the probability of finding the global solution. However, it's not guaranteed or even able to prove that a global solution was found. Another advantage of the solvers in the Global Optimization Toolbox is that they can handle very tough problems, those that are non-smooth or discontinuous, like the plot you see in the lower right, for example, as well as problems that have undefined gradients or otherwise stochastic in nature. I found through my industrial research experience that most engineering problems will require a global approach that is capable of handling multiple problem complexities. For example, if your problem has absolute values, if-then statements, or state-switching logic, they'll certainly fall into this sort of a category. For now, let's take a look at a few of the factors that can help guide the decision on which algorithm to use. Clearly, there are a wide array of algorithms available to support a diverse set of users and problem types that span multiple industrial sectors, ranging from biopharmaceutical, financial, industrial automation, aerospace, and automotive. And there's an extensive amount of documentation that you can sort of get a feeling for here, which includes guidelines for helping you decide what would be an appropriate choice for a particular problem. However, just based on my own personal experience, I've come up with a simplistic flowchart that can potentially expedite the selection process for common engineering problems, such as the HEV fuel economy maximization effort discussed so far. Regardless of how one chooses an algorithm, careful attention will typically need to be made to at least the output space, meaning whether it's a single minimum and differentiable or not, the number and type of variables, the number and type of constraints, whether they're linear or not, and of course the number of objectives, if it's a single objective or multiple objective type problem. As well, correspondingly, the available resources that you have at hand. For example, if you're working on your own local laptop or a high-performance computing center, certainly could influence your algorithm choice. In the case of the HEV problem, either the genetic algorithm or the pattern search methods would be appropriate, and I have used both with nearly identical results. However, because I have access to large-scale computing resources and because I plan to solve more complex scenarios in the future involving integer constraints and multiple objectives, I've chosen to use the genetic algorithm. Since I've chosen to use a genetic algorithm, I thought it would make sense to explain a little bit more behind what a genetic algorithm is for those who aren't so familiar with it. A genetic algorithm is a meta-heuristic optimization and search method belonging to a larger class of evolutionary algorithms. And as the name suggests, the algorithm uses mechanisms analogous to those found in biological evolutionary processes. The algorithm begins by creating a random or is otherwise seeded with an initial population of design candidates. The individual candidates are simulated and evaluated with respect to one or more objectives. Individuals in the current generation are then used to create the next population through a process of selection, crossover, and mutation. More specifically, to create the new population, the algorithm performs the following steps. Individual design candidate scores of the current population are determined through simulation and its fitness values via a cost function. Scales of the raw fitness scores are made to convert them into a more usable range of values. The algorithm then selects members called parents based on their overall fitness values. Some of the individuals in the current population that have lower fitness values are chosen as elite. These elite individuals are passed on to the next population. The algorithm produces children from the parents. These children are produced by either making random changes to a single parent, also known as a mutation, or by combining the vector entries of a pair of parents, known as a crossover. These will replace the current population with the children to form the next generation. The algorithm will then stop only when one of the stopping criteria are met, either, for example, a change in tolerance has not been sufficiently satisfied or a maximum number of generations has been exceeded. More details of the genetic algorithms used by MathWorks and the many options available for configuring them can be found at the website below. So I just mentioned that the genetic algorithm will require or otherwise create an initial design candidate population. In the case of the HEV study, I used a Sobol quasi-random space filling routine from the statistics toolbox so as to maximize the available design space while ensuring an even yet non-correlative sampling of the specified design variables. For large-scale and computationally expensive problems, it is often good practice to explore the design space in just such a manner, either through the form of sensitivity study to determine which variables are most significant, or Monte Carlo sampling and things of that nature. This will also help you gain confidence that your simulation will efficiently and successfully run under a wide array of parameter combinations. The script that I used to generate this figure and the initial population is available on MATLAB File Central by searching for createdoe.m as shown here. Aside from gaining additional insight with respect to how the genetic algorithm is initiated for this particular case, I would like to emphasize that, like a design of experiment study, given that I do have a significant number of predetermined design candidates that I can evaluate simultaneously, I'd really like to run as many of these designs in parallel as far as my computing resources will allow. And indeed, the genetic algorithm will take advantage of the parallel computing toolbox and MATLAB distributed computing server should you have access to those software tools. To that end, please allow me to provide a brief overview of what each of those products are. So the Parallel Computing Toolbox is an additional product that will allow for the full use of your computer hardware capabilities. For example, when you start an instance of MATLAB on a multiple core machine, you see something as described in the picture here, where you have one full instance of MATLAB running on one of your threads or one of your cores, and it's going to be on top of the base OS or whatever it happens to be, Windows, Linux, what have you. However, with Parallel Computing Toolbox, you will allow MATLAB to have access to the full capabilities of your hardware and OS. When you invoke it, you'll automatically open up additional so-called workers on each of these additional threads. In addition, you get high-level tools for interacting and monitoring your hardware resources. If I were to switch to MATLAB, I can show you some examples of this here. So you'll notice the Parallel tab. I already have a few profiles defined. For example, local will be whatever machine I'm operating on. I have an Amazon Cloud account profile established here. There's a MathWorks public cluster set up in our headquarters that I have access to, and there's a Windows Server machine down the hall that I could also connect with and just deploy jobs to, so I choose. There's a whole API behind the Parallel Computing Toolbox, so if I wanted to find a new cluster object, for example, I could type something along the lines of my cluster is equal to par pool, and I can at this point invoke one of the profile names, for example, MathWorks public, and the number of workers I'd like to open up and prepare for interactivity with. I could say 48 different workers, and I'll go off, and you'll notice in the bottom left that a pool is being established. At this point, some interactive protocols are being invoked, and the individual workers are being made available to my session of MATLAB here, so I can actually deploy and send parallel jobs off to those workers, and MATLAB will maintain their status and acknowledge the work being done there, and also feed them more jobs as resources become available. Okay, and at any time I can close that back down through command something like this, delete the current profile, and it's going to shut it back down. So aside from providing high-level tools and infrastructure for the creation and monitoring of jobs and allocation of hardware resources, the Parallel Computing Toolbox also is a bridge to cluster hardware. So far what I was talking about primarily was concerned with working on just local machines. However, if you want to scale up your job to multiple machines, then you will want to use a tool called MATLAB Distributed Computing Server. which basically takes the parallel computing toolbox to another level. Whereas now, for example, you have your job running on multiple workers or multiple threads on your local machine, you can actually make a connection to a remote machine or sets of machines and deploy and invoke multiple sessions of MATLAB on each of those threads as well. Once that's been established, you can switch from your local profile to a cluster profile and interact with your MATLAB session just as you would before, but instead of using local resources, you'll be using remote resources. So the approach I took when trying to scale up the HEV optimization problem from my base laptop, I basically started with the laptop version itself and prototyped the code and made sure that everything was working okay. Certainly that you'd want to have some checks to make sure that the simulation was going to be robust. So I went ahead and did that, and that was relatively easy to do. Windows platform, shared common file space, pretty straightforward. Of course, there's limited scalability. I have a dual core, with each core being able to represent 2 threads per core. So next logical step would be to scale it up, and there happened to be a high-performance Windows server box down the hall that I could log into, use remote desktop, and there was 40 cores available to me, as well as sufficient memory to run all the jobs simultaneously. Certainly a lot more powerful because it's a consistently Windows operating system between my laptop and this machine. It was very straightforward and easy to get up and running. Obviously a little more expensive than a typical laptop machine, so as you can imagine, things start to get more expensive as you scale up. And from there I went to scale up another level using the Amazon Elastic Cloud Computing, and I'll show you in a moment how that looks, but the idea is basically you set up a machine remotely, you're able to connect a remote session through your MATLAB terminal and coordinate the workers, monitor jobs, and so forth. And that's obviously considerably more powerful than working with your basic laptop or desktop machine. It's kind of convenient because you can start it up on a moment's notice, more or less on demand, and it's still relatively low cost, at least compared to the infrastructure and IT resources needed to maintain a high-performance computing center of some kind. So that is a service that's in our early adoption phase. There's a link below that you can look at if you are interested in learning more about that type of a service. In the meantime, I'm going to show a quick demonstration of how that works by shifting over to my browser. And you can see I have a cluster already online that I've brought up and established, but at any time I could go ahead and create a new cluster. I could give it a name, choose the number of workers up to 256, and there's a few different machine configurations that I could choose from depending on my memory and disk space needs, and then there's different versions of MATLAB available that are available on the image. And once I'm happy with all those things, I could go ahead and create a cluster, and then in a short while the hardware will be found, the image will be booted up, and I'll be given host names that I can incorporate into my parallel computing cluster profile. So if I go back to the cluster I have online, for example, I can go ahead and download that profile. I'm going to copy it over to my MATLAB working directory, and then I can proceed to import it. Okay, so now that it's there, I could go ahead and validate it, although I'm pretty confident that it's going to work, so I'm not going to bother with that step for now. What I can actually go ahead and do is launch a job. This is a script that I'm using to package up the HEV model itself and initialize the optimization process. It will take some time for it to collect the files and upload them to the machine into the shared filed workspace, compile the executable, and distribute it amongst the individual workers. However, I can still go ahead and at any time monitor jobs on any of my profiles that I might have defined. So if I go down here, what I would expect to see shortly is an updated status of the job running. So now that the files have uploaded, I can indeed see that the job is available, and from there I can interact with it. For example, I can queue it for diary. If there were any errors on the job and things like that, I would get some diagnostic capabilities to investigate what might be going on with the job itself. If there are other users that I had given access to with this profile, I could see the jobs that they had submitted and manage it all from this main client interface here through my MATLAB window. Now that I've explained how the job submission process works, let's go ahead and take a look at some of the results that have come back. What I'd like to show is the convergence process of individual populations from one generation to the next. And so what we'll see in a moment is an animation showing the individuals from a given population as their equivalent miles per gallon performance increases from one generation to the next. So I'm going to shift over to MATLAB once again, and I have a quick script I can run that will show exactly that. And what you'll see in the figure is an evolution from one generation to another, and what we would want to see is this overall convergence of the miles per gallon equivalent increasing, as that was the maximization goal. So I'll play it once more. And you can sort of see that as the generations increase, the individuals within a population, the overall mean tends to be maximized as intended. We can look at it another way and also ensure that we are getting good convergence through the trajectories from one generation to the next. So for example, here's my overall average miles per gallon equivalent score as a function of generation. You can see it's quickly, because of the large population size, is going up and then pretty much flattening out. However, I can see the individual design variables go through initial transient, and then we see nice convergence, giving me confidence that the values I've arrived at are indeed have converged nicely. So for wrapping things up here, just to compare the before and after of the optimized supervisory mode transition tables and regions, you can sort of see an overall improvement of about 9.4% as the engine is pushed off to higher speeds and lower torque values. There's a few different reasons for why this has happened. In particular, it is an older engine, and based on data from an engine technology from about 10 years ago, it's also a larger engine compared to the powertrain size. So we would expect naturally to see sort of the engine not making much sense to use until much higher speeds and torque ranges that would be appropriate. So it's an interesting result in a sense, because one would maybe naturally also want to think about doing vehicle design optimization in conjunction with the control as well, so that maybe there would be a more optimal gear ratio or other types of engines that one could explore, and that would certainly lead to an integer type constrained optimization challenge. So as I mentioned, definitely getting higher speed, more efficiency in the power split zone. And I think most compelling is the reduction in computational time. So taking a problem that would have taken serially on maybe my laptop of approximately 27 days and being able to reduce that down to half a day is quite compelling. I mean, I don't think there's many people out there that would attempt to go through with a challenge that would take 27 days just to run one nominal design set. But through the power of the parallel computing toolbox and computing resources like the Amazon Elastic Cloud, we're taking these types of problems that were probably intractable and making them quite amenable to an average engineer's workflow. Throughout this webinar, the application of model-based design has been applied to an automotive optimization and problem involving relatively complex software and physical dynamic systems. Utilization of such workflows provides opportunities to not only enhance performance but test and detect issues early. And through the use of Simulink project, data dictionary, and version control integration, collaboration and sharing of models in a team or enterprise environment has never been easier. While model-based design methodologies do require an upfront effort, such investments are quickly capitalized through model reuse. For example, using the same models for multiple development purposes, such as system design, control development, tuning, and validation, as well as real-time deployment of algorithms and physical models for hardware verification and testing. Furthermore, when one invokes the power of parallel and cluster computing hardware, to develop models such as the HEV1 presented here can be utilized to solve problems that may otherwise be too computationally intensive to tractably solve. This concludes my talk. Thank you very much for your attention.